I showed you the Bob Fella video, right? We're going through the paper and whatever, the motorcyclists and the baseball. Well, like this one, what you have is you have these two discs that are probably like paper discs, but they're rotating. And they probably have it so that when they're rotating, that there's some line, let's say, from the center to there on both of them. And so what I'll know is as they rotate, this is at some point, like that part right here is going to be over there, and then over there, and then over there. As it goes around, it's going to be rotating. I'm trying to make it so the bullet is going to go through here, go through this one, and then go through that one. Well, if they went through them at the exact same time, let's say with when that line was at 12 o'clock, if it went through at the exact same time as that, then they would look the same. But what's going to happen is if this goes through at 12 o'clock, then there's time while the bullet is going from here to there, there's time for this to continue moving, so it's going to be at a different angle than this one. All right? And that's how we're able to determine the speed of the bullet, based on how much time we can figure out the time to go from the time that the bullet went through the first disc compared to the time that it took to go through the second rotating disc. So we have, they're separated by 0.850 meters. So this right here, they're separated by 0.850 meters. And they're rotating with an angular speed of 95 radians per second. So 95 radians per second. And it's a constant speed. They're moving at that speed. It's not like we turn them on and then they start from rest and they're going at that speed. So the speed isn't changing. That's how fast they're going. So if that's how fast they're going, then what's the alpha? What's the angular acceleration? 0. So the alpha is 0. So that means that I can call the omega, either omega O or omega F. I'm going to call it omega O. And it's giving us the theta, that the displacement, the difference between how much where this line is compared to where this line is, the difference is 0.240 radians. So that's how. So in the time from the time that the bullet went through the first disc compared to when it went through the second, that one's going to be 0.240 radians ahead of that one, where the bullet is, because it had that amount of time more for it to still be rotating. So the theta is 0.240 radians. And all I have to do is use those facts to solve for the time. And if those are my facts, my equation is my equation is theta, equals omega original t plus 1/2 alpha t squared. So that's the formula that I'd be using. And the alpha is 0, so 1/2 alpha t squared is 0. Makes it easier to rearrange to solve for time. Time is going to be theta divided by the original angular velocity. And if we plug in the numbers, we'll get the time. So the time is going to be 0.240 radians divided by 95 radians per second. So that's going to be a small number. And the radians will cancel out, and I have seconds in the denominator of a denominator, so we'll put it in the numerator. So what is 0.240 divided by 95? 0.003. I need more. That's only one significant digit, so I need more than that. 0.003. 0.00253. So now that I know that, well, we're assuming that the bullet's going at a constant speed, that we're I don't know whether it says ignoring air resistance, but in general, we're not factoring in most straight line motion problems. We don't factor in the air resistance when we do them. So that means that it's taking that amount of time to go that distance. And we're looking for the speed of the bullet. So if I take that number and divide it by that, I should get my answer. So for speed, I am going to use V. So V is distance over time. And so the distance is 0.850 meters. And the time is 0.00253 seconds. Sort of a clever way of actually figuring out the speed of a bullet, right? Using the idea that things rotate, and if we have them rotating and starting at the same point where the mark is here, well, if that's there and then later on it's there, there's a difference, there's an angle difference, and from that angle difference I can get the time. And what do you get for that? So 336.4, so 336 meters per second. And that was number 22. Just curious, what did I say? Well, I said 337, so something might have been rounded, maybe a little bit different. Maybe for some reason, I only used 0.0025, and maybe that gets it to 337 instead of 0.00253. Any questions?